Hi dear students, good morning to all. Myself Bhavsai Sononi, Assistant Professor, Department of Chemistry, Gokul Education Society's Arts, Commerce and Science College, Jawar, District Palakkad. Dear friends, in the previous part of the video, we studied about a first order reaction. We also tried to derive the equation for the rate constant or the velocity constant of the first order reaction in integrated form, and we came to a equation for the first order rate constant is k is equal to 2.303 upon t log to the base 10 of a upon a minus x. A is the initial concentration of the reactant, x is the concentration of the product form, and a minus x is the concentration of reactant left unreacted. Dear friends, based upon the same, that is first order reaction, in this part of the video today we are going to study kinetics characteristic or the kinetic characteristic of first order reaction. How we can study the various characteristic of first order reaction with the help of rate equation. Definitely it includes the various characteristics like unit of the rate constant of first order reaction, half-life period of the first order reaction, and the graphical representation, which is very important to predict the first order reaction of chemical reaction. So the first characteristic is the unit of rate constant of first order reaction. How we can predict the unit of rate constant for the first order reaction? Here the terms, because the equation for the rate constant of first order reaction is k is equal to 2.303 upon t. I hope you got this. Upon t log to the base 10 of log to the base 10 of simply a upon a is the initial concentration, a upon a minus x. A minus x is the concentration of reactant unreacted after time t. In this equation, with the help of this equation, we are going to predict the unit of rate constant for the first order reaction. In this equation, the term a upon a minus x, term a upon a minus x is the ratio of concentration, so it is the ratio of same term, so definitely concentration divided by concentration will get cancelled, and the 2.303 it is the constant value, hence the specific reaction rate or the velocity constant k has a dimensions of only the reciprocal of time. That's why the unit of rate constant for the first order reaction is in the form of reciprocal of time. So if the time is given in the second, so the unit will be per second. If the time is given in the minute, unit will be per minute, per hour, per day, per year, etc. So remember that the unit of rate constant of the first order reaction will be always the reciprocal of time. So it will have the units like per second, per minute, per hour, etc. Again, second characteristic of the first order reaction is that it is possible to calculate or to determine the time required to complete the definite fraction of the reaction. So here we are able to calculate, we are able to determine the time required for the completion of definite fraction of the reaction, or simply the half-life period of first order reaction can be calculated with the help of same equation k is equal to 2.303 upon t log to the base 10 of a upon a minus x. First of all, this we should know what is the time required to complete the definite fraction of the reaction or the half-life period of the reaction. So time taken to complete the definite fraction of the first order reaction is always a constant, and this time required for the completion of definite fraction of the first order reaction is again independent of initial concentration of the reaction. So this time required for the completion of definite fraction of the first order reaction does not depends upon the concentration of reactant, remember. And the half-life period of the first order reaction, or the half-life period, is the time taken for the initial concentration of the reactant to become half of its initial value, or to reduce to half of its initial value. It means that suppose the initial concentration is the 100, then how many time is required to decrease this concentration to half of its value. So to decrease 50, this much time is called as the half-life period. Again, this 50 will be decreased to 25, and whatever time is required to become 25 from this 50 value, then this time will be called as half-life period, and this time will be exactly same. That we will discuss with the help of some equation here. Dear friends, here you can see here that is half-life period is the period or time in which the concentration of the reactant is reduced to half of its initial value. Suppose here the half-life period of first order reaction is indicated by means of pen T suffix 1 by 2, and you know the condition, that is the final value or the final concentration of the reactant becomes half of its initial value. Its initial value is A, and this becomes, so this X is becoming the half of its initial value. So X will be equal to A by 2. So this is the condition for the half-life period. That's why this equation K is equal to 2.303 upon T log to the base 10 upon A minus 6 can be rearranged in the form of time as T is equal to 2.303 upon K into log of A upon A minus 6 into log of A upon minus 6. So we will put T 1 by 2 instead of T and A by 2 instead of X. Just very simple. So whenever X is equal to A by 2 and T is equal to T1 by 2, then this equation can be rearranged as T1 by 2. T is replaced by T1 by 2 is equal to 2.303 upon K into log of A will be as it is A minus X. X is replaced by A by 2 again. So after simplifying all these terms, we will get T1 by 2.303 upon K log to the base 10 of this log to the base 10 of 2, because it is very simply A upon A by 2. That's why it will be simply log of 2, and the value of log 2 is 0.3010. By multiplying these two digits, these two figures, we will have the multiplication of this 2.693. That's why finally we will get the equation for the T1 by 2, means the half-life period of first order reaction is that T1 by 2 is equal to 0.693 divided by K, and this equation for half-life period of first order reaction suggests that the half-life period of first order reaction is constant and it is independent of the initial concentration of the reactant. Remember that the half-life period of first order reaction is constant and it always independent of initial concentration of reactant, and hence it follows that for the first order reaction the time taken to reduce the initial concentration from 1, it should be 1, from 1 to 0.5 mole per dm cube is the same as the time required to reduce from 0.05 to 0.025 mole per dm cube of the reactant. So whatever time is required to reduce the concentration from 1 to 0.5, it will be same to that time, to that required for the concentration to reduce from 0.05 to 0.025. So this time and this time will be exactly identical because these times are called as half-life period. Next characteristic of the first order reaction is called as a graphical representation, because it is possible to predict the order of reaction with the help of graphical representation And this is one of the important characteristic how we can predict, how we can determine the order of reaction or the value of rate constant with the help of graphical representation. Dear friends, we are already having the equation for the rate constant of first order reaction as k is equal to 2.303 upon t log to the base 10 of a upon a minus 6. If we will rearrange this equation, then this equation can be written as k into t, because this t will be multiplied to this and it will be divided to this. Definitely it will be written as k into t upon 2.303. This log a upon a minus 6, this is the term which is just like what, log of a upon b. Log of a upon b, it can be simplified as log of a, remember that already we had used this, log of a minus what, log of b. Log of a upon b can be written as log of a minus log of b. That's why this log of a upon b is written as log a minus log b, because a minus 6 is stated as the b capital B based upon this mathematical equation. Again, I am going to transfer this term on this side, so it will be having positive sign. So log of a minus 6 is equal to, it will be transferred on this side, it will be having then negative sign, minus k upon t into k upon minus k into t upon 2.303 plus this term log of a. So this is the simple equation, log of a minus x is equal to minus k into t upon 2.303 plus log of a. Dear friends, if this equation is compared with the equation of straight line, y is equal to mx plus c. So this is the equation that represents the equation of straight line having y-intercept log a and the slope will be minus k upon 2.303. How it can be decided, how it can be calculated, that we will discuss in the next slide. Just so this equation is the equation of straight line, y is equal to mx plus c, and whenever we will plot the graph of log of a minus x, log of a minus x versus time, then it gives a straight line. It gives a straight line with negative slope. It's very important, with negative slope and positive y-intercept, and this y-intercept is equal to log of simply a. So this is very important. So on the y-axis it will be log of equal to, this y-intercept will be equal to log a, and the slope of this line will be equal to minus k upon 2.303. And once we will calculate the slope, from the slope definitely we will be able to calculate the value of k by just multiplying it with the 2.303. So this is the way by which we will be able to calculate the value of rate constant of first order reaction with the help of this characteristic. Dear friends, again this equation means the equation k is equal to 2.303 can be also rearranged as k into t divided by 2.303 is equal to log the base 10 of a upon a minus x, instead of simplification of log a minus log b. So this equation, whenever compared with the equation of straight line, then this equation indicates the equation of straight line y is equal to mx, and the plot of log of a upon a minus x versus time gives a straight line passing through origin with the slope is equal to k upon 2.303 without y-intercept. And once the slope is calculated for this line, from the slope the value of rate constant or the velocity constant of the specific reaction rate of first order reaction can be also calculated with the help of this equation, k is equal to 2.303 into slope. Sometimes this equation for the first order reaction, for the rate constant of first order reaction, can be also modified in another form at two concentration of the reactant at two time. That can be simply, so this equation for the first order reaction can be also written in the form of K is equal to 0.303 upon T log to the base 10 upon A minus 6. This equation can be rearranged, or it can be written for the time as T is equal to 2.303 upon K log to the base 10 of A minus x. Dear friends, in this case, suppose if we are having the two time, that is definitely the concentration is the initial concentration will be same, but at time t1 the whatever product is formed, its concentration indicated by x1, and after some time the amount of product formed or the reactant reacted is indicated by means of an x2. So we have the two concentrations x1 and x2 at two different time intervals t1 and t2 with the initial concentration of A. Then the equation for the first order rate constant can be also modified as like this. So here we will be able to write the equation for this T1 as, so for T1 it will be 2.303 upon K log to the base 10 of A upon A minus x1, and for T2 2.303 upon K log to the base 10 of A upon A minus x2. If we will take the difference of these two equations, that T2 minus T1, then it will be written simply as 2.303 upon K log to the base 10 of, just written nothing but the log A minus log B will be equal to log A upon B. After simplification, this A and this A will get cancelled. Definitely T2 1 upon this divided by T1 divided by 1 upon T, so it will be A minus x1 divided by A minus x2. And if we can write this equation for rate constant of first order reaction K as 2.303 upon T2 minus T1 log to the base 10 of A minus x1 divided by A minus x2. It means that we are also able to determine the value of rate constant of first order reaction if the two time intervals are provided, or if the two concentrations of the product or the concentration of reactant reacted are provided at two different time intervals T1 and T2, then we will be able to calculate the rate constant of that reaction. It means that if the values of x1, x2 at T1, T2 are provided, then we can calculate the value of velocity constant or the specific reaction rate of first order reaction. So dear friends, today in this part of the video we tried to study all the characteristics of first order reaction which are very important to predict or to determine the rate constant of first order reaction or the rate of first order reaction. So in the next part of the video we will talk about the second order reaction, which is also one of the important another reaction, and we also discuss the derivation for the rate constant of second order reaction with its rate constant. So we'll resume in the next part of the video to study about the second order reactions. So thank you very much.